All right, there we go. Thank you all very much for coming, particularly at the end of the conference. I know you've all gone to lots of great talks, and I appreciate you coming to mine, particularly at the end of the show when I'm sure you're all a little tired. This is New Java Performance Puzzlers. If you were here last year, I did a talk with a very similar title, Java Performance Puzzlers. And we're going to do more or less the same thing, but we're going to update a bit. Like last year, I'm going to do some interesting benchmarks, and we're going to see what we can learn from them. But I'm going to focus on stuff that was added in Java 8, Java 9, and actually a little bit of Java 7. And some of these things are actually pretty low level, and some of them are very popular, like streams and lambdas. And we're just going to see what their performance impact is, but more importantly, see what we can just learn about thinking about performance. So to do this, first we need a good way to measure. I'm going to use JMH, the Java measurement harness. If you don't write micro benchmarks all the time, like I do, you may or may not be familiar with this, but it was created by a gentleman named Alexei Shopolov, who was formerly at Oracle doing performance evaluation on new JVM and language features, and is now at Red Hat working on performance evaluation of the Shenandoah collector. And this has become the de facto standard way to benchmark the VM. And that's true not just for Oracle, but also Oracle's Graal research team. We use it at Azul. I think IBM uses it, I'm not sure. But it's become the way we benchmark the VM. And the way you write a JMH benchmark is basically kind of like a JUnit test. You just annotate your methods with benchmark instead of test. And then the harness takes care of a whole bunch of things. Specifically, the harness takes care of a few problems that you might run into if you tried to write a benchmark yourself. If you came to my talk earlier, we talked a little bit about how the VM warms up and starts off in the interpreter phase. And if you just wrote a short-running test and just measured the interpreter phase, congratulations, you've proven nothing. Because you would only continue running in the interpreter phase if that piece of code is cold and doesn't matter to the performance of your application. You need to run it for a while to make sure it gets to C2, where we're going to be in the optimal phase, and that's where all your hot code should end up if I did my job correctly. The other thing that JMH will do for you is, when you're writing this sort of thing, you have this tendency to need to write a loop, because you're measuring things that are often very short, and you can't measure time down to that resolution. And so you do it in a loop. But then the JIT might get a little too clever and do some loop optimizations that skew your results. It might just say, I only need to run the loop once because the result is the same every time. JMH will take care of that sort of thing for you. And the one that sounds the coolest is it has this thing called the black hole to prevent something called dead code elimination. So in a simple benchmark, you can just return a string. So I'm going to start off with string concatenation. But if you got a more complicated example, like you're trying to consume every element in an array, you can use black hole and say black hole consume. It just sounds fun, doesn't it? All right. So let's start with streams and lambdas. Or just a stream, I suppose. All right, I could do a summation of a for loop. I could use the old C-style for loop. Or I could use, say, the enhanced for loop from Java 5. Or I could use a stream over the integers and just do a sum on an int stream. Now, if you came to the talk last year, you'll know that there's actually a very strange corner case if there's a call inside the loop where B might be faster than A. That's just mad. But, of course, we all love lambdas, and we really want to know if C is as good or better. If you went to Oleg's Graal talk earlier, then you'll know that, unfortunately, the answer is no, but Graal is doing better. But we're going to come back to that a little bit later. The unfortunate truth is you're not incorrect to worry about this sort of thing. At the end of the day, a compiler, honestly, is just kind of a big, crazy pattern matcher. Like, simplest optimization is something called constant folding. 2 plus 2 is 4. So I saw a constant, I saw a plus, I saw a constant, I generated a reduction to 4. That's just a regex, right? It's just our tokens, our constants, and binary operators, but it's just a regex. Now, you've all probably written a regex before. You had some log file you had to process, right? And you wrote that regex, and it worked the first time for every single file you ever gave it. No, of course not. You gave it one file, you sat there and beat on it for half an hour until that file worked, and then you gave it a second file and it broke again. That's kind of what a compiler writer's job is. We've got to recognize one pattern and then another pattern, and so if you give it a different pattern, it does occasionally tend to fall over. I mean, we give it a large corpus of programs, but we can't cover everything. And just to illustrate that, I'm going to start with the same example I used last year. I want to take a number and I want to turn it to a string. I could use integer toString. That's slightly slow. I'm not going to do that. So I could do it by doing concatenation. I could do concatenation against the empty string. I find this one really ugly for some reason. I don't know, it bothers me. But we could do it that way. Or we could use a string builder. I like integer toString. I find it the most aesthetically pleasing, but integer toString isn't the fastest. So alternatively, I could use a string builder. I could just create a string builder, append num to it, and then call toString. That would be an equivalent operation. JMH will give us a way to compare these two things. So I'll show you the benchmark. Here it is. I've annotated it with how much I want JMH to run it. I'm going to have it fork the VM 2 times. The default is 10. I'm going to have it do 2 warm-up iterations that it's going to throw away. Again, the default is 10. I'm going to do 10 measurement iterations, or 5 measurement iterations. Again, the default is 10. And I'm going to measure the average time in nanoseconds it takes for each of my benchmark methods. And I'm going to do concat. That's one of my benchmark options, and builder, that's another. And I'm just going to give it a random integer. And if I want to run it, I use Maven to compile it into a jar file, and then I can just say run, in this case, example 2. It's actually the class name, but it's a pattern, and I can just specify the first part. And it will go and do this. It's going to take a while, so we're not going to sit here and watch it. And if I let it do 10 forks and 10 warm-up iterations and 10 measurement iterations, we'd be here for like 5 minutes, and it really wouldn't be very exciting. But I just want you to get a feel for how this works. It's trying to be very thorough in a way that you might not be if you tried to do this yourself. Okay, so if you know anything about string concatenation and how it gets compiled, it actually, by Java-C, gets turned into a string builder. The bytecode is that thing there. If you don't like bytecode, and I wouldn't blame you, it's this. New string builder, append the empty string, append num to string. So it's just using a string builder, right? And it's actually doing 2 append calls rather than 1 append call. So it should be slower. Or we should be tied. No, neither of those is the correct answer. In fact, concatenation is faster. And not by a tiny amount, at least in percentage terms. It's about 10 nanoseconds faster than the string builder. How does that make sense? How is 2 append calls faster than 1 append call? Well, the answer is we didn't do an append. What? No. Certain versions of VM have an optimization called optimize string concat. You can guess what it does. But it very specifically pattern matches string concat. The fact that I assigned the builder to a variable is enough to confuse it. In example 2, if I get my bytecode exactly the same, it will actually optimize B. But it very specifically looks for a particular pattern. If it isn't that pattern, the optimization does not kick in. And this is a real problem when you're dealing with a compiler. So that optimization is inside the JIT. And it's actually something JRocket had for a while before that, and then it was sort of copied into Hotspot, but now we've decided we want to do something better in Java 9. So in Java 9, if I do the same concatenation, I get a very different piece of bytecode that I can't even really quite write in Java, to be honest. Java 8 is now option A. It does the 2 appends like we just saw. Java 9 turns into this. It's a get static of our field, num, and then it's an invoke dynamic call. What is dynamic about string concatenation? Well, what it actually does is it at runtime produces a specialized function just for doing this concatenation operation for you. And it says make concats with constants, and it just takes an integer. So it actually bakes the empty string literal into the function, and the only variable coming into the function is our integer. That's the thing that actually varies from each execution. This is done for you in Java 9, if you recompile with Java C. And it does actually make a significant difference. Now we're another factor of 2 faster. I have to be a little bit careful here because there's more going on. You have to be very careful because you have to actually recompile this. That's actually very different from what we've historically done in Java. Normally, the bytecode has been sacred. We just don't touch it. Maybe for ill, when you think about what we did for generics and we have type erasure and, oh, that's awful. But we've never really wanted to touch the bytecode. And now with this, we're actually changing the bytecode of concatenation to use a new built-in JDK capability. That does mean you have to recompile all of your code to get the benefit. So in like 5 years, I think this is going to be really, really awesome once everybody switched over to Java 9. Well, fortunately, there is another thing in Java 9. There are multi-version jars. So you can actually put Java 8 and Java 9 code into one jar, and it'll pick the right one. I don't know how many libraries are compiling with that yet, but this might be a reason to do it. All right, let's take it one step further. Let's do an extra append, num1, num2. And Java 8 comes out to be pretty much what you'd expect, 4 append calls. Java 9 is another make concat with constants. It takes 2 integers now. How many of these are there? Actually, infinitely many. This is what's called a polymorphic signature function. You can't write them, but they've existed in the VM since Java 7, and they nominally take object array and return object. But really, their signature can be absolutely anything. And so it will produce something that does integers, and of course, we have baked in the 2 string literals. And again, it's faster by almost a factor of 2. Pretty cool. Does require recompiling. There is one other optimization that may be going on here that's a little hard to separate. Java 9 also has something called compact strings. I probably could have turned it off and we could see which one is winning. But they're both coming into play. Java uses UTF-16 strings, at least that's the default representation. But it turns out many strings are Latin 1 and don't need to use extended characters. So in Java 9, we actually changed the internal representation of a string to be a byte array, which can be single byte per character if you don't contain any extended characters, and it'll expand to 2 bytes per character if you do contain extended characters. And the benefit of this is that the strings are all smaller. They're faster to concatenate because they're half the size. They're faster to relocate when we have to move them around because of garbage collector, because they're half the size. And this is a very nice optimization. That might also explain the performance difference. You have to be very careful in isolating which effect is which. And the other thing you have to think about when you look at this is yesterday's good advice can be today's bad advice. You might have heard in the past, just don't use string concatenation. Well, now, if you've got a long series of concatenation calls, that's actually perfectly fine. Those get optimized pretty well. Even in Java 8, that was true. In Java 9, it's even better. Although it did cause a bug. Did anyone see this? Where if the left-hand side of your concatenation operation contains a side effect, we'll actually double the side effect in Java C. Oops. But, you know, these things happen. But now concatenation is pretty fast. That doesn't mean you should always use concatenation, unfortunately. It's never that easy. Never. String builder isn't actually obsolete. Let's say I were to put this concatenation inside of a for loop. I'm going to do the first, I think I did 10,000 character or numbers, and I just essentially joined them together. Versus doing it with a builder. Well, the builder still wins. I think we'll say by a large amount, by a factor of 20. So there are situations where the builder is still better if there's a loop involved. If it's a simple expression, you're probably good enough with concatenation. And the builder can actually go a step further. If you approximate the size of the array that's backing the builder, you can actually avoid creating underlying temporary arrays and avoid producing a bunch of garbage. So you can go further. It's not a simple, yes, this is always good, no, that's always bad. It just doesn't work that way. So we've seen how various patterns can trip up the VM. We've seen that this optimized string concatenation was looking for a very specific bytecode pattern, and if it didn't see it, it didn't optimize well. Now, unfortunately, lambdas are a significantly new pattern in some respects. Not nearly that simple, but they produce lots of little intermediate objects for the lazy evaluation of the streams, and those are actually a bit hard to handle. Graal has put a lot of effort into partial escape analysis to handle this well, and that's part of why Graal is doing better on this sort of thing than OpenJDK is today. We are also doing the same thing at Azul. And so the unfortunate truth is, for this simple example, when I tried to run it on, I think I used JDK 8, I flipped around a lot between 8, 9, and 10 when I was putting this together, to be honest, and they all kind of came out the same. But the streams example was almost an order of magnitude slower. So, lesson here is, don't use streams. No. You got to ask yourself, how much should I worry about this? Is this a huge problem for me? I can't tell you. It depends on where we're looking in your code. So recently, I came across this article by Stackify about Java performance tuning tips. And strangely enough, unlike almost every other Java performance tuning article I've found, I didn't hate this one. I actually liked the suggestions. And the first two suggestions were, don't optimize before you know it's necessary, and use a profiler to find the real bottleneck. This isn't new advice by any means, but it's correct advice. This is pretty much just the advice that Knuth gave us long, long ago, just applied to Java. And I think we do a lot of evil in the name of not doing premature optimization is the root of all evil. We're often forgetting a lot of the other context of that quote. Just looking at the whole paragraph makes a big difference. He said, "Programmers waste enormous amounts of time thinking or worrying about the speed of non-critical parts of their programs, and these attempts at efficiency actually have a strong negative impact when debugging and maintenance are considered." We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up opportunities in that critical 3%. So, the question about whether or not you should use lambdas is it in your critical 3%? I have heard a horror story from someone where a junior programmer went to their critical method right after Java 8 came out, and changed it to using a lambda, and performance dropped precipitously. But the lesson isn't that you shouldn't use lambdas. The lesson is you've got to monitor your critical 3%. Most of your code is not that critical 3%. It really is like 1 in 50 methods or 1 in 50 compilations that actually affects your performance. And you need to know where that is and monitor it if you really care about performance. And if it's not in that, it's not usually a big deal. Now, there are wonderful tools for this. I'm not going to spend a lot of time talking about them today. There is JRocket Mission Control, which has flight recorder, which used to be a commercial feature, is now free to use. And you can get a table view of the hottest methods in your system after you've taken a recording. Very nice. I personally really like the work of Brendan Gregg at Netflix, who makes these flame graphs, because I like visualizations, which is why I did talk about visualizations this morning. I like being able to see the big system at a glance. I like being able to see that, oh, I spent 10% of my time on that. That's strange. He, in one of his talks, actually gives an example of, we're running UTF-8 encoding. Why are we doing that when we're not actually encoding in that, and finding an interesting bottleneck that way? So I think having this sort of view is important. Finding that hot 3% and focusing your attention there. Looking elsewhere really doesn't matter. I'm not impressed by you speeding up the code you run 1% of the time by 90%. Woohoo! 0.9% gain. Not that big a deal. And you know what? If you like something a lot, we will make it faster. Think about it from my perspective. You're all my potential customers. I would like you to buy my VM. You all like streams. How do I get you to be my customers? I make streams faster. What about that other guy that likes that other weird thing? I don't know. There's only one of him and 100 of you that like streams. The hell with him. I'm going to focus my attention on the largest audience, the largest corpus of code that I can make fast and make it better for you. And just to illustrate, we are willing to go to great lengths to make things fast, even things we don't think you should be doing. All right, so say you have a not wonderful developer on your team who thinks that flow control is terrible and null pointer exceptions are awesome. Yep, we've optimized that. And this has been around for a long time. So I've got a program. This is it. It constructs 3 different arrays of 100,000 objects, well, 100,000 references, some of which are objects. I do this once and have 10% roughly being null, and then 50%, and then 90%. And I have these counting routines that count the number of NPs. And I actually copied the code because I want each one to get JITted separately so that they're independent optimization opportunities. But it just runs through the array, calls toString, and in this particular count function, it also adds the null pointer exception to a hash. And so at the end, we'll have about 10,000 elements in our hash set, right? Maybe. And if we don't happen to add a new one, we'll print out the stack trace just to see. So I'm going to run this. Okay, there we go. So with the run that did 10% of them being null, out of 100,000, we caught 9,979 exceptions. That sounds about right. And there were 9,900 unique ones. Okay, it's a little bit of a discrepancy, but not huge. Okay, if 50% are null, so about 50,000 were caught, only 21,000 distinct exception objects. Okay, and 90% were null. Okay, 90,000 caught, but only 38,000 unique exception objects. What is going on here? Well, we optimized the throwing of null pointer exception by creating a singleton null pointer exception to reuse. Oh, and by the way, since we're using a singleton, and it might be called, this method might be called from lots of different places, we couldn't really have a truly correct stack trace. So, and you know what? Filling in stack traces is actually the slowest part of creating an exception, so let's just not do that. So at the top here, this is the printing out of the stack trace of a place that is throwing lots of null pointer exceptions in your code. You don't get to have one. And I think this is pretty fair. If you as a Java developer are this bad, we will make your code run fast, but we won't tell you where your problem is. You get to live with those as consequences for what you have done. But the point of this is, of course, not that we optimize hot exceptions. It's that if you like something enough, even something as evil as throwing null pointer exceptions all the time, which, why? We will optimize it. In a previous talk, I showed causing uninitialized class exceptions to happen over and over again. And that's actually something OpenJDK hasn't fixed, but we encountered it enough at Azul that we actually decided, okay, fine, we'll fix it. We just don't want to think about it anymore. We will do this, even if it's quite pathological. So because you like lambdas, we are working on making them faster. They are already faster in Graal. Many of the cases are faster in Azul's VM with our new JIT called Falcon, and we're working on making them that much better. You like streams? I really like streams myself. I want to see them be fast. And of course, the other nice thing about streams is if you have to, you can go parallel. You shouldn't do this for a tiny stream, but if you have a really big collection, you can go parallel, and that's a much easier change to make. I think that's nice. All right. So basically what I'm saying is, in the right place, a lambda might be a bad choice because it is performance critical. But that doesn't mean you just shouldn't use them. That's not what you should take away from this. But there are little things we could do with lambdas and streams that would make a bit of a difference, And more importantly, they won't do any harm. And that's actually an important distinction. Think about it from my perspective. I am writing an optimizer. What do I optimize? How do I know the critical 3% of all your pieces of code? I don't. So I just make a best effort at absolutely everything. But it's important that I not make anything worse. You would not be happy if I made something worse. But we're never going to truly reach optimal. We're just doing a lot of small changes all over the place, and sometimes very big changes, to make things generally better. And this is actually tricky on its own. The new Intel chips have AVX512 instruction set, and they handle really big pieces of data quite efficiently. But when it switches to AVX512, it lowers the clock speed. That works fine if your data is AVX512. But let's say you did some AVX512, and then you switched to doing something that's not AVX512, and the processor's now running slower. That can create a performance problem. And this is the sort of thing that I actually have to worry about. We're really trying to balance a lot of factors. So let's look at something simple that wouldn't do any harm. Let's talk about a lambda. Stream for each, and I'm going to go to system.out.println. Well, not quite. So I could do system.out.println and just do it with a method literal, or whatever Java calls these. Or I could use a lambda that takes an argument and call system.out.println. Those are the same thing, right? Or I could do it the old way. I could use an anonymous inner class and just say new consumer and println that way. There is actually a difference here. Now, I didn't want to have the I/O overhead of doing this test, so instead of going to system.out, I decided to set out so that it sends everything to the black hole. No I/O overhead, but I also know that we're actually really going to walk through this loop. And here are the results. System.out.println is actually, the method literal is actually a touch slower than the handwritten lambda. A touch. I mean, it's only 300 nanoseconds, so I'll give you that. But why, or 500 nanoseconds, but why would that be? There is actually a difference in the bytecode here. And fortunately, the ugly thing, the anonymous inner class, is the slowest. The difference is the capture. When you write system.out::println, you're capturing the lambda before you call it. You're capturing system.out before you call it. Versus if it's inside the lambda, you reevaluate system.out every single time. And that latter one might sound worse, but it has an unexpected benefit. Because system.out is being looked up, we have no capture state from the surrounding scope. And we can actually use a singleton lambda that we reuse every time and don't have to create a new lambda object every time we run this loop. With the other one, system.out is captured before the call at the construction of the lambda, and we can't create a singleton, and it runs slower because of that object construction. And of course, that's also putting pressure on your garbage collector. The difference isn't significant in terms of throughput, but it might be significant in terms of garbage. But again, this still isn't to say that lambdas are bad. In fact, Peter Lorre did a talk on low latency in Java 8 where he describes what he's created at Chronicle. He's actually created this thing called Chronicle Wire, which is for serializing and deserializing data. And he actually uses lambdas heavily. He just uses it in a stylistic way to make sure that to minimize this problem. So if you know where your performance bottleneck is, you can exercise a little more energy and probably find a way to make it work for you. But you just got to know where your bottleneck is, know where your performance is going to be, and spend the time. If this isn't that hot part of the code, don't worry about it. Basically, as always, it depends. 15 years ago, I used to work at a company that did DNA and proteomic data. Let's just say DNA sequences are large strings. 500,000 characters was common. Millions of characters was common. And then we would take those fragments and line them and make even bigger ones. And we actually used something very much like the Streams API to process this, because we couldn't actually load our entire data set into memory on the workstations we were using at the time that only had 256 megs of RAM. So that was a very demanding for its time application where we used streams, and we actually had to use anonymous classes. But it worked. It all depends about what problem you're trying to solve. And another problem we had there, as you might expect, is you want to display this DNA sequence. Okay, that's a bottleneck. And we did spend a lot of time figuring out how to write our code just right to render a DNA sequence quickly to our UI. But the rest of the system, we didn't so much have to worry about. That was a place that really mattered. So let's poke a little deeper. Other things that make a difference that have been added recently-ish. So let's talk about doing a call. I could do random next int. I could create an int supplier around random next int. Maybe I could use reflection. That's probably going to be the slowest option, although reflection is actually pretty heavily optimized. If you keep calling the same method object over and over again, the JDK will actually dynamically generate a dereflection class underneath to do that call and optimize that. Or in Java 7, I have method handles. And I can just do it this way. It does the access check at lookup time rather than invoke time. Or I can even do a bound method handle where I bind to this so I don't have to pass it in every time. And you won't be surprised between C, D, and E which one of those is fastest. The bound method handle is actually tied with a normal call or a call through the Lambda or the interface, whatever you want to call it. The regular method handle is pretty close, even though I have to pass in random every time. And reflection, despite all the cool optimizations I just described, is actually the slowest, although not by much. I mean, it is, I guess, 20% slower than a normal call. But that's probably not as bad as you thought it was. If I have a lot of code using reflection, should I rush out and switch to using method handles? I would probably say no. I mean, if you can do it, fine, but it's not urgent by any means, unless it's just super hot. You can also use this to access fields. You can do a getter or a setter and do the same binding. And okay, it's not as fast as just directly accessing a field. But it is faster than reflection. One thing that is a little unfair about this test to reflection is having to box the integer, whereas the other options are not boxing, but that's actually kind of one of the benefits of method handles. So you could argue this is unfair, you could argue this is fair. It just depends on what's common for you. Are you returning objects or are you returning primitives? But Java 9 added an option E to that list. It added a VARHANDLE, which actually doesn't appear to be any faster than reflection. So why did we add this? I'm sorry, I'm going to say var. Many people will say var. I think the word is variable, so I'm going to say var. But it's the same basic thing. And we could already do this with method handles, and they appear to be faster. So why did we add this? Well, it's not quite the right question to ask. It's not about the setter and getter so much. but about other things. VARHANDLE has a lot of capabilities the other APIs do not. Array element VARHANDLE. I can actually have a VARHANDLE around an individual element in an array. Or I can get a byte buffer VARHANDLE over a field where I can see the individual bytes and manipulate them. That I couldn't really do from a public Java API before. And that is actually something people do. If you are using something like that does off-heap, which many of the things you use do, Hazelcast does it, Spark does it, then you need this sort of API. And before they were using unsafe. Now there's actually a public way to do this. And more importantly, VARHANDLE does many other things related to atomicity and visibility. It has more flavors of Git than you can imagine. Get volatile, get opaque, get acquire, get and set, get and add, get and bitwise and, get and bitwise or, get and bitwise XOR. You get the idea. And these all have different interesting visibility characteristics. And then there's even compare and set, which lets me say, if the value is this, change it to this. This is the concurrency building block. And that's why we added it, as a way to do concurrent collections. I'll admit I tried to benchmark this some myself, and I found it kind of difficult. So I'm just going to go to the source, or who I'll regard as the source, Alexei, who created JMH and did a lot of the benchmarking of this. And what he found is the oldest way we used to do this was through Atomic Updater in JDK 6. And even up to 8U66, it was the slowest way. 8.7 versus 6.7 for unsafe. In 8U92, things got a little closer. And then by Java 9, we're looking pretty good. So I guess we didn't really need to do this. Well, no, it's still nice to have a public API with these capabilities. And if you actually went and looked at the source code of Java Util Concurrent, you'd find out that it's gone through this kind of interesting evolution. Java Util Concurrent used to use atomic field updaters as of Java 6. But because they were hard to optimize and were a bit slow, in Java 7 they switched to using unsafe. But, that's the JDK code. It's okay for them to do that, but you shouldn't do that. As of Java 9, now that VARHANDLEs are around and they're just as fast, the Java collections now use VARHANDLEs, which I think is very nice. We have this public API. A lot of things can start to use it rather than using unsafe. Spark can use it. Hazelcast can use it. JC utils can use it. All sorts of things can use it now that were before relying on unsafe, which I somewhat understand why Oracle doesn't want to keep supporting, because it was never a public or stable API. Now, I do want to say, when you're looking at this sort of stuff, you should trust but verify. In my research, I found that people were saying that atomic field updaters had been updated to use VARHANDLEs underneath. I've looked at the source code. I can't see that that's true. Maybe in certain versions it was, but what I'm looking at right now in OpenJDK, I did not see that. So don't just assume. If this is performance critical for you, go and check. And for the last thing, we're going to go really, really small. Single instruction, small. But it still matters in the right context. Which would you think is better? While not some condition, thread yield. While not some condition, thread sleep for a millisecond. While not some condition, thread on spin wait. What is that? Well, that's actually something that my company added, so I'm a bit biased on this. We added this as part of JEP 285. It was added for Java 9. And what it is that method with the right JDK and JVM is an intrinsic that gets turned into an Intel pause instruction, which is a special instruction on Intel chips for optimizing spin loops. Single instruction. That's it. But it's there to have the program wake up quickly without consuming a ton of power. And since I'm biased, I decided to go and look at someone else's results, Mr. Boson, whose talk I actually wanted to go to this morning, but I was speaking at the same time. And he actually did a benchmark of this with JMH, so I thought I'd just use that instead. And on-spin weight comes out in 47 microseconds, I believe, and versus yield is 143, and then the sleep is just really slow because it's actually a sleep for a millisecond. I'm like, really? Does any of this actually matter? Well, a lot of things do spin loops, waiting on queues, particularly if you're using something like disruptor or low latency messaging. So it does matter in the right context. Should most of you go out and use this right away? Probably not. But it all just depends. Should you go put a lambda in your hot loop? Probably not. You just have to think about what you're doing. So just to summarize, I'll admit, the new stuff isn't always fast. Lambdas and streams, unfortunately, are maybe not as fast as you'd like them to be. But you can find ways to use them. Just because that code isn't hot, or by constructing things a little bit differently, like Chronicle Wire did. And then a lot of new things we put in seem stunningly low level, but we put them in for a reason because in the right place, they really do make a big difference. But do keep in mind, premature optimization is really the root of all evil. You're just wasting an enormous amount of time on code that doesn't matter. It's fun to go play with these things, and I actually think you should. Just don't do it in your production code. It's all about, to paraphrase something from US real estate, location, location, location. If this is hot code, it might matter, both for good and bad. If it's not hot code, it doesn't matter, both for good and bad. So, if you really care about performance, what I really want you to remember is go identify your bottlenecks. Take out a profiler, figure out where they are, and don't actually even assume they're going to stay the same tomorrow. You got to track them constantly and check performance. And if you don't have to worry about performance that closely, that's perfectly okay. There's nothing wrong with that. But if you do care about performance, don't just go switch everything from string concat to string builder or vice versa. It probably doesn't matter. Find the place where it does matter and fix that, and then move on to more interesting things. All right. Well, thank you all very much for coming. I hope you learned a little bit about what's been going on under the covers in Java 7 and 8 and onward. And if you'd like to know more, please go check out the articles here, which give a far more detailed write-up than I can give you in 50 minutes. Thank you all for your time, and I'll be around if you'd like to ask questions.